Today we are going to see opamp working as an integrator. Not only a simple integrator, it is an active integrator. Why it is active? Because we are giving some gain. Now this is just an ordinary normal integrator where this is your R 2.2 kilo ohm I have applied, and this is the capacitor that we have taken 4.7 nanofarad, and the V0 will be 1 minus SCR, and this I just given for the offset value, nullifying the offset voltage. Now what I am going to do, I am going to apply V input as 0.1 sin omega t, and I am just going to keep the input voltage constant and change the frequency. I will change this frequency and I will jot down this output voltage here in this column, and this column will calculate our gain. Now what will be output gain will be, this will calculate our log scale gain, V naught by what will be what is V in nothing but 0.1. 0.1 means 100 millivolt. What we are going to set? We are going to set the function generator as 100 millivolt, and we are going to start from 50 hertz. Why 50 hertz? Because our function generator working do not work well at 1 to 50 hertz. Means it don't give a constant input voltage. Suppose if we apply input voltage around 2 hertz, then at 40 hertz or 50 hertz it is not going to be the same. So around 50 to 1 megahertz it will be same. So we are applying from 50 hertz. Now we are going to connect the circuit, and after that we are going to learn about the integration function. Now if you see, this is the circuit, this is the biasing I have done with the green wire the positive biasing and the blue wire the negative biasing. This is your opamp, and this is the feedback C 4.7 nanofarad, and this is your 2.2 kilo ohm, and if you see, this is your for the nullifying the offset voltage, that it is connected to terminal 3, and here we are supplying the input, and from here we are taking the output. Now let us zoom on the DSO. Now let me show at lower input, this input that we have applied around 100 millivolt, and what output we are going just a saturated value. Now when I increase the frequency, see there is fluctuation, that's why I am taking from 50 hertz. If you go to 50 hertz, and after 50 hertz there will be much fluctuation in the input. See, our output came to 21 volt. And with the increase in frequency there will be a decrease in voltage that we are seeing. Now if you go to 100 volt, now 100 hertz, now slowly I am going to 100 hertz, there is decrease in the voltage. Now with the increase in frequency we are going to observe the decrease in voltage. Now I am going to 500 hertz. If I go to 500 hertz, then there is a 3 point around, if I go to around 500 hertz, see it is around 2.80. Now if I go to 1 kilohertz, now let me go to 1 kilohertz, see the voltage has decreased to 1.60 volt. Now I am again increasing my range of frequency. Now if I go to directly to 2 kilohertz, now around 2 kilohertz it is changed to 800 millivolt. Now we are going to look up for the frequency where input and output matches. Now if you increase to 5 kilohertz, now let me increase to 5 kilohertz. Now also it is 360 millivolt, around 5 kilohertz. Now I will increase to 10 kilohertz. Let me increase to 10 kilohertz. Now it is coming around 200 millivolt. Let me increase this input range. So around 10 kilohertz output is 160 millivolt. Still it is not equal. Now let me change the scale. Now slowly if I increase, see around 14 input and output are almost same. If I increase slowly, say 104 and 104 millivolt, means around 100 millivolt we have. Now if I go to 20 kilohertz, now 20 kilohertz we have got 84 millivolt. Now what we are going to see, we are going to just see the plot between frequency and the amplitude that we got. Now if you see, this is the frequency that we have taken, this is the output voltage that we got around that value, and this is the gain, how gain has been calculated. If you see, this is 20.4 by 0.1 because 0.1 we have given the input. If you see the formula of dB, it is 20 log this value, 10 to log this value at the base of 10. Now I am going to plot between frequency and the gain. Now if I select this one and gain in dB, and after that go to insert, and if you go to insert, there you are going to see the chart. You click on the chart and you got this one. Now what we are going to do, we are going to change in the change in the logarithmic scale. So go and select this one. There I will get a format axis, and here if you find there is a logarithmic scale, and this is your Bode plot. Let me zoom to this picture. Now if I zoom to this picture, then we are seeing that this is a straight line. This is a straight line that is going to cut here. Now if I am going to extend it till 1 kilohertz, then this will be extrapolated and it is going to cut around the open loop gain of opamp, which is around 140. That's why our function generator was not working well within this region. That's why I have taken from 50 Hz. Now if I want to show in till 50 Hz, go to format axis, make this minimum to 50. Now if you see, now you got, this is just a integrator, means anywhere you are going to get integration. But what will happen if I am going to integrate around 500 Hz, then your gain will be around 30 only. As long I am increasing the frequency of the signal, you are going to get the decrease in gain, means integration will be happening but gain will be decreased, means it will be acting like a normal RC integrator. There is nothing like an active RC integrator in this one, because with the increase in frequency there will be decrease in gain. So here our purpose is not fulfilled with your normal RC circuit. So, but now we are just going to see the integration happening. Now one point you need to note down that this is going to cut around around 15,000 Hz. Our input and output are matching. Input was 0.1 volt and our output, this is gain is around 1 dB. Now this is 20 Hz. Now let me get that point. Around 15,000 Hz, the gain is around 1 dB. This is in dB. So around this one, this is cutting. So we are just going to look how this value has come. So going to DSO. Now before going to DSO, let us think about this point and this point. Now I told you we have started from 50 Hz and there was this one. Now I have extrapolated and this is certainly going to cut your open loop gain. This is around 114 dB for this IC. Now what will be this point? This is a point of concern where our gain is unity. This is your 0 dB. In practical it is means 0 dB equivalent to 1 gain, because 20 log 1 it is going to give you 0 dB. Now if you see the V0 equation is minus 1 by SCR into V in. V in, what we have said, we are taking just the magnitude 0.1. If you multiply 1 with the 0.1, you are going to get this value. This sign is coming because of this inverting operation only. Now if I see this is 0.1 by SCR, now where our output is going to come around 0.1, when this value SCR will be equal to 1. When SCR is equal to 1, it means S will be 1 by CR. And we just need to calculate this frequency point. What is this S? S is nothing but J omega. If I take the magnitude only, this will be omega. So omega will be 1 by CR. And what is the omega? 2 pi F by 1 by CR. F is equal to 1 by 2 pi CR. So this will be the frequency that is cutting. Now we have seen that around 1500 we were getting around 0.98 dB or 0.98 dB we were getting, means a gain of around 0 dB we were getting around 1500 frequency. Now we are going to calculate this point and we are going to see. Now for this what we have taken, C is equal to 4.7 nanofarad and R we have taken 2.2 kilo ohm. Now if I calculate this one, F is equal to 2.2 into 10 to the power 3 into 4.7 into 10 to the power minus 9, you are going to get a value around 1540. Now here around 15,000 we were getting this value. Now calculated value is 15.400 means 15400, and practically how much we got? 15,000. This is the, there I was saying wrong, it was the 15,000, and here the theoretically value came around 15.400 means 15400, and here 15,000. So this is what we got it. Now we are going to see that almost between these ranges you are going to get almost at every point the integration. So if we are going to provide this square, you are going to get the output as a triangle, that we are going to observe in DSO. Now you see that around 200 Hz, there is a peak to peak 9.5 volt, and there is a perfect integration is happening. If I increase the frequency, now you will get a smooth integration. See, this is the integration of that square curve is happening. Now this is what we were talking, anywhere between this frequency, I am just changing the frequency. You see the magnitude is also reducing with the increase in frequency. Now let me increase the range of frequency. If I increase the range of frequency, still the magnitude will be decreasing. See, magnitude has come to 2 volt. As long as I am increasing the frequency, magnitude will be decreasing, but your perfect integration will be happening. This is same as the RC integrator. See, this is the perfect integration that we got. Now in the next lab, the practical RC integrator, that is called active RC integrator. There we are going to see how to keep the gain almost a constant or a bit little variation.